Hello and welcome to the fourth module of Machine Learning and Data Science course. So today it's going to be mostly theoretical talking, most of it, and no coding or no examples and practical demonstrations as of today. So before getting into it, because it's going to be relatively short topic to discuss, but we'll get into it. But before going into that, let's discuss what we have discussed so far in different modules overall. So we started with the very basics of Python and introduction to the course. Then we moved a little bit towards machine learning libraries like NumPy and Pandas, Matplotlib, Seaborn, and all these things. While discussing all these, we saw examples how different applications can be made from these libraries, why we use these libraries and everything. We understood all those things. Then we started working with data and we understood how data is classified and how we can actually collect data through different sources and other than relatively easily available data. And then we understood a little about exploring the data without even getting ahead and starting with the model. And other than that, how we analyze it and clean, manipulate, do various operations on the data so as to get better insight of what we are going to be working with. So all these things we have already seen, and finally a little, very little on dimensionality reduction, feature selection, and all these things. So by far we haven't started with the machine learning domain per se, but we have actually covered a lot in terms of dealing with the data and understanding it and all these things. So these basically are the foundational topics that I would like you to have, kind of like the prerequisite that I was talking about, like a little bit on statistic, calculus, and all these things, mathematics, alongside having a little bit intuition about data. So now, if I say the word data, you will have a striking in your head about a data frame, like a 2D matrix and something like that. And now that I talk about EDA, you will know what I'm talking about, what I mean by manipulating or rescaling and all these things. So these all are kind of like the prerequisites to better understand machine learning. So just bear with me for a while because it's going to be just theoretical for now, from now on for the rest of this video, and it will be relatively short. I hope you learn a little bit what I'm trying to get through you. So let's start discussing on the very fundamentals of machine learning. So before even getting to the first slide, I want to discuss the approaches that people take while starting to learn machine learning. So like any other domain, there are two approaches to understanding machine learning or start to learn machine learning. The first one being the top-down approach, another one is the bottom-up approach. So what is the difference between these two? So top-down approach basically means that you start with the models, you start understanding what machine learning is, then directly you jump into understanding the models. Then you start to implement those models, then you see that there is some underlying mathematics behind it. So you might either be applying all these models using libraries, or you might either be applying all these models knowing the math behind it. So if you look deep into it, then you'll understand there's some underlying mathematics. So what you do, you start exploring those mathematical concepts, you start understanding how these models actually work and all these things. So this is basically the top-down approach. So what happens is that the top-down approach basically puts you somewhere in the middle of understanding, because you jump in the middle, that is understanding the models, then you jump behind on the earlier concepts like the underlying mathematics and understanding how data works and all these things. Then you again jump back to that part where you were exploring the model, implementing it, and then you move ahead of that step. So it puts you in a situation where you have to go from to and forth between different topics basically. So the other approach that people take is the bottom up approach. So what you do there is that you start with the very basics. You start with understanding basic concepts like matrix, linear algebra, and all these things. Then you move a little bit toward broader topics like hypothesis testing, statistic, probability, and all these things. So basic concepts. After that, you move to some more complex concept like eigenvectors, eigenvalues, and ANOVA test and all these things. Then you start understanding the data, and then you finally land on different models, regression model, classification model, supervised, semi-supervised, all these concepts. And finally, when you have a better understanding of all these things, then you jump into different models and go into depth with them, because now you already know the maths, so you can actually get ahead and go ahead and start to implement the models from scratch and understand all those implementations on your own. So yeah, these were the two different approaches that people usually take. So what we aimed for was that give you a little intuition already, so that you start understanding the models. You don't have to jump back and stay there in the very beginning by understanding matrices and all those things. So we started from a point where you have a basic intuition, so that the terms that you'll be listening or the terms you'll be reading throughout, when you go through the broader topics and get into much detail about them, so all those topics and all those terms won't confuse you now. So you can move in a relatively better way. So the very first thing is understanding the difference between traditional and machine learning approach. So what happens in traditional programming? Now just for a minute, think of a function that you write in any programming language. Or forget it, let's think of a function in mathematics. For example, let's say y is equal to 2x square plus 4. So what is this function? So this function is a set of rule, or just one rule for now, because it's just one statement that says 2x square plus 4. And what is x here? X is the data that you're going to pass to that function at different instances. So we have the set of rules, we have the data. So what we are going to do with this? So we are going to put the value of x. For example, let's say x is equals to 1. So we had 2x square plus 4. Now we are putting 1 into that, so it becomes 6, because x square is 1, x square of 1 is 1, and 1 into 2 is 2, plus 4 is equal to 6. So it gave you an answer. So putting the data through the rule is going to give you answer. So that's what traditional programming does. We define the set of rules, we provide the data for that rule, and then we get answers out of it. So for example, if you're programming a sorting algorithm, let's say bubble sort, in any programming language, what are you doing? We are actually defining the set of rules that takes the input as an array. The data here is array, and the set of the statements that we write for bubble sort, or the rule that we write for bubble sort, is the basic rule of the function. So we give it an array, and then we get an answer which is a sorted array. So the unsorted array is the data, the rule, that the function that we write in any programming language is the rule, and the answer is the sorted array. So now we understand what traditional programming looks like. Or many of you already did understand this, but just a recap for that. So how does machine learning differ from it? What does machine learning do differently? So what we do is we tell machine learning that go back to the let's go back to the example of mathematical function y is equal to 2x square plus 4. So what we are going to do is say that, hey, here's the value 1, the data is 1, and the answer for that data is actually 6, right? Because 1 maps to 6, because we right now know the function. So let's say that we don't already know the function. What we are going to get is that we are going to get 1 and we are going to get 6, because 1 is mapping through that function to 6, but we don't actually know that function. So what we do, we provide machine learning with various instances, like 1 maps to 2, 1 maps to 6, and 2 maps to 2 square is equal to 4, 4 into 2 8, and 8 plus 4 is 12. So 2 maps to 12, and so on and so on, because my math is not that good, so let's keep it to that. Or let's say a regular function, or very simple function of y is equal to x square. So x square here is the rule, x is the data that we are going to provide to that function, and y is the answer that we are going to get out of the function. So 1 maps to 1, 2 maps to 4, 3 maps to 9, 4 maps to 16. So yes, my maths is a little good. So yeah, that is the basic mapping of y is equal to x square. So what we are going to provide the machine learning algorithm or machine learning model with. So we are going to give it 1, we are going to give it the answer 1, we are going to give it 2, we are going to give it the answer 4, and so on and so on. So we are going to give it various instances so that the machine learning model can look at it, so it can start to think that okay, 1 maps to 1, 2 maps to 4, 3 maps to 9. So what is happening here? So the machine learning will start to understand the basic pattern or the basic mapping of the data to the answer. So what is this mapping that the machine learning model is trying to understand or trying to learn? It's again the rule that actually governs this mapping. So if we put the data through the rule, we are going to get the answer, right? So if we provide the data, we provide the answer. The machine learning model has to be capable or is actually capable to understand that mapping and give you the rule that actually maps that data to the answer. So, do we expect the machine learning model to give us the output as x square or y is equal to x square? Actually, no. We don't expect machine learning models to give out the actual function as the output or actual rules as the output. What it does is it understands that rule that y maps to y is equal to x square or x maps to y in the following way, but it doesn't actually provide you with that rule. What it does is stores the rule in its own terms, in terms of weights and biases and all those things. And whenever you again try to ask it, so you learned something. Now let's say the machine learning model learned something. Now we want to ask the machine learning model, hey, you just learned that this is the mapping between data and answer. Now I have a data, but I don't know the answer for it. For example, let's say 21534, and we don't know the mapping that what answer are we going to get from that data. So what we'll do is we'll say that to the machine learning model, hey, here's the data. Now you already have learned the rule. You aren't going to tell me the rule, but at least tell me the answer that I'll get for this data. So what the machine learning model will do, it already knows the rule. We have just provided it with data. So it will start to map that data onto the rule and then give us the answer as output. So, what did we understand so far? We understood that rules and data are provided in traditional programming to get the answers. And in machine learning, what we do is we provide a set of a set of data and answer pairs to the model or machine learning algorithm. It understands it tries to understand the rule that governs this mapping, and then whenever asked a question about the data, it again tries to give us the answer using the rule and the data that it has now. So that's going to be the basic difference between traditional and machine learning approach. So, how is machine learning classified? Machine learning actually is so let's just understand the hierarchy. So, artificial intelligence is the topmost level of that hierarchy because machine learning, deep learning, neural networks all actually come under artificial intelligence itself. So, machine learning is a subset of artificial intelligence which uh, which works in a certain way. And now deep learning, which is relatively newer than machine learning algorithms, is actually a subset of machine learning itself. So artificial intelligence is the top of the hierarchy, and then there's machine learning, which is subset, and then there's deep learning, which is again a subset. So these are the three basic levels in which you can actually understand the classification. So how is machine learning or how are machine learning models actually classified? Machine learning models can broadly be classified as supervised, unsupervised, and reinforcement learning. But as the time has grown, we have come to realize that these are the very basic kind of the very basic kind of classification that we can perform, but the classification is much more diverse than just these three classes. So for example, there's a hookup between supervised and unsupervised learning, which we call as semi-supervised learning as for now. And then there's of course deep learning, neural networks, and all these things. But let's just start to understand supervised learning by what it means and how what it tries to do. So supervised learning, as we already saw in the last example, what it does is it takes the data and it takes the answer. So the key to supervised learning is that we are going to tell the model, or we are going to provide the model with both the data and the answers. So supervised learning basically means that we are supervising the learning by telling it that here's the data and here's the answers. So how does unsupervised learning differ from it? In unsupervised learning, what we do is we don't actually know the answers. We only know that there is data. So what we provide to unsupervised learning is just the data. So how is it going to learn? So for supervised learning, it's relatively simple because we already have an intuition that data and answer have a mapping between them, and we want to learn that mapping using the machine learning model, or use the mapping rather. So supervised learning basically does that. So what does unsupervised learning does? We give a very large data, or a very large data frame, let's just say, or data points, various data points to the unsupervised learning model, and say that there's an underlying relationship between these data points, and we want to get that underlying relationship out of that data. So what happens is that, let's just say that the world actually is very rich in terms of data right now, and data is growing very very rapidly, because every year the data just gets twofold each time, or every year. So with all this data, what happens is that not no single entity on the planet actually knows how to actually deal with all this data, because that data actually contains various answers. For example, if you're an ad company, what you want to do is you want to target your ads to your specific audience, or your specific niche, right? So how will you find that niche where your ads work? You'll take the various data in terms of supervised or unsupervised manner. Let's just say we are going to take it in unsupervised manner by just taking that where your ads work, and where your ads don't work. So we want to understand if your ads are working in some specific area or not. So for that, what we can do, we can collect the data relative to ad. For example, if the ad is posted on some website, so if we can understand that some user is actually spending how much time looking at that ad or browsing that ad, we can note that time somehow. Let's just say somehow we can do that. Then we can store that, and then we provide this data to the unsupervised learning model. So for example, if I'm saying that a person spends just 5 seconds or 3 seconds on a particular ad, so would you say, or just by thinking, would you tell me that the person is interested in that ad? Probably not, because 3 seconds is not a very long time to look at an advertisement. But if I'm telling you that the person is looking at the advertisement, for example, 1 minute, 2 seconds, or 3 seconds, then your answer might change, because that's relatively a long time to look at an advertisement, right? So what we just did is, or what we just saw is, an example of unsupervised learning, because we actually didn't know if the ad was working or not. We only knew that there is certain data that has an underlying meaning to it in terms of that ad working or not working. So what we did, we provided the machine with just the data and not the answer. So our data was the time that was spent on that ad, and the answer that we didn't knew was that if the ad is working or not, right? So just looking at that data, we can tell actually if the ad is working or not. We don't need the answers right now. So this is just a very basic example of unsupervised learning. Another example, and a relatively very popular use of unsupervised learning, is in spam detection. So spams don't come with a tag that they are spam or not, right? So what happens is that Gmail, Google, and Rediff Mail, and all these uh, email service providers, what they did was, they employed unsupervised learning techniques and started to understand that how a spam is structured, or what defines a spam, what are the qualities that define a spam. So whenever we get a new mail, they look for those specific attributes that define a spam or are present in a spam, and on that basis they start to classify it as a spam or not. So what happens is that we can convert that task into supervised learning. How? So once we start to detect that a particular mail is spam or not, we start to tag that mail with a value. So let's say 1 is for spam and 0 is for not spam. So we keep on tagging mails over time, and we start to store that in a database. Now what do we have? We have a mail, and we have a tag if it's spam or not, right? So we have the data, that is the mail, and we have the answer, right? We have the answer if it's spam or not. So now we can train a supervised learning model over that same data, and we can get a better understanding of how spams can be classified, right? So we just saw how unsupervised and supervised learning kind of work in a harmony, right? So other than that, there's reinforcement learning. What reinforcement learning aims is it that let's just say you are playing a Mario game, right? So when you are playing Super Mario for the first time, and you're just on the very basic level, one of one is it's called, so right, so you're on first world and the first stage of the first world, and you're trying to move ahead in the game, right? So when you're doing it for the first time, or you were doing it for the first time, probably you were 4 or 5, or some of you might be a little older by then. So yeah. So whenever you were trying it for the first time, did you actually make it through the entire game in the first try? No, right? So you probably yes for some, but not for me. Okay, so yeah. So that is the general consensus that you didn't make it through the first level in the first try, or through even 5% of the first level, or maybe you did. So yeah. So it took you many tries and many iterations for you to start to learn the pattern that if you jump here, it would work. If you didn't jump here, it wouldn't work. So what happens is that when you're playing Mario, you're moving ahead in the game. So at certain points, if you get killed, you start back at you go back to the start, right? So that is a kind of penalty that the game actually governs on you, or game actually implements on you, that whenever you get killed, you move back to the start, and whenever you actually finish the level, the game actually rewards you by moving you to the next level. So this is the basic idea of reinforcement learning. We put a Mario, or we put an agent in a certain situation, or in a certain game, or a certain environment. We let the Mario explore and learn on its own that how this world actually works. So in the Mario example, the world is the entire first level or the game, and then the agent here is the player or Mario itself. So the computer starts playing by itself, and then it starts learning what works and what doesn't. And whenever something works, we reward it in a way that it understands, okay, this is working, and if something doesn't work, we actually penalize it by telling it that this doesn't work and you will have to pay a penalty for that, right? So this is the basic idea of reinforcement learning. Another thing is a mixture of supervised and unsupervised learning. The spam example, where what we did was we tagged certain spams. Now, whenever new spam came, what we did was we put down all the new spams together. We put down the old spams with the tags together. Now we have some data that is actually labeled and some data that is not labeled. The new data isn't labeled and the old data is labeled, because we found out that those are spam or not spam using the earlier technique, unsupervised learning. So when some of the data is supervised and some of the data is unsupervised, that is called as semi-supervised learning, because it actually aids the unsupervised learning process by actually having some tag data or some supervised data. So yeah, that is the basic idea. Now, for you to get a little frightened or get a little, no, not disheartened actually. So yeah, this is one of the deep learning models for. Okay, so I probably shouldn't have chosen this as the first image to show you for deep learning, but yeah, just to give you an idea of what deep learning models look like. So deep learning models, or neural network models, are actually an analogy to the human brain, or how human neuron system or nervous system works, right? So what happens is that there are various neurons which keep on shooting information in our entire body. For example, if I touch a surface, if I close my eye and touch a surface just by the skin, I understand the kind of surface I'm touching. For example, if I'm touching water, I would understand the that I'm touching water just by the properties of it. If I'm touching wood, I would have some idea that it's wood or not, right? If I'm touching metal, then I'll have an idea what the metal is supposed to be, right? So what happens in my body? There are certain neurons present in my body that start to fire whenever I'm touching metal, and there are certain neurons that start to fire when I'm touching water, right? So this tells my brain that this neuron has fire, so it must mean this. or this or a certain neuron has fired, so it must mean this. So deep learning models or neural network models, they aim to do something similar. What they do is they are set of neurons which form layers, right? So this is one layer, this is another, and all these small things that you see are different and different layers of the model, the entire model. So each and every layer consists of various small tiny bits known as perceptron, which are an analogy to the to a specific neuron in human body. So what each neuron or each perceptron does is it takes an input. For example, my finger touching the surface is an input, and it fires or it doesn't fire depending on its firing. Basically means it gives an output as one, it's switched on or it's switched off by being zero. So by doing that, it tells the neural network that, or the entire brain, what you might call this entire brain, that this works and this doesn't work. And based on that, from here to here, we get an output telling me which kind of surface I'm actually touching. So here, this is my finger which is touching the surface, and here, this is my brain which tells me this entire thing is my brain, and this is the output that I get, what kind of surface I'm touching. So this is a basic analogy of how neural networks work. But in practical understanding, no one actually knows how networks work. Not even the best of the best or the founding fathers know how neural networks can actually be architectured. What do I mean by that? People do already know that neural networks work because of a certain reason, that neurons fire and don't fire, but they don't actually know how to actually construct a good neural network. So how did one come up with that? This is actually a trial and error process, a heuristic process that people go through by experimenting and by understanding that what works or not. So if I just remove this layer, this might not actually work. But why is it not working? No one actually knows. If I add a certain layer or a group of certain layers somewhere here, will it work? We can't actually know it for sure because we don't actually know how to construct neural networks in a specific way. What we have to do is we have to stack different layers, and we have to keep on experimenting and trying to understand what works and what doesn't. So this basically has given rise to certain standard neural network architectures which are employed for different tasks. For example, there's an architecture called as convolutional neural network which works for images. There's an architecture called as the time series data. There's recurrent neural network, LSTM, and all these things. So employing what would work on what kind of data is known, but how to employ it in which certain way, nobody knows. That's a heuristic topic, and that's still to be explored by scientists. So the field is constantly growing, and each day we are getting new advancement in the field, and we have started to understand it better and started to construct new and better models day by day. But it takes actually a huge amount of computational power to train bigger and better models. So what is the difference between a neural network or a traditional machine learning algorithm? When should we use one, when should we not? So the convention is that, or experimentally, it has been found that when we have limited data or very less data points, then we should go for traditional machine learning algorithm because they tend to perform better with lesser amount of data. But when we have huge amount of data and we don't want to go through the pain of understanding the underlying facts of the data, because in what we can do in deep learning models is that we can just put an image through here and we can directly get the output here, that if it's a dog, it's a cat, or something like that, right? So we don't actually have to do any operation with the image per se because it's an end-to-end model. So yeah, that is the basic idea of neural network, and why and when it should be used. So it should be basically used when there's plenty of data, and by plenty of data I actually mean lots and lots of data. For example, good models train on millions of data points at a time. So yeah, that amount of data, then we go for neural network. So does that mean that we shouldn't actually train neural networks on the thousand data points or lakhs of data points? That actually doesn't mean that we shouldn't train it on the lesser amount of data, because we can actually train it on less amount of data, but it might not actually give us that level of accuracy. And again, this is an end-to-end model. So what we mean by end-to-end model is that we don't have to go through the pain of understanding the image, and we don't have to orient the image or something like that. uh, a dog can be in a horizontal picture, a vertical picture as well, right? So we don't actually have to analyze it. We directly put the image, we get the answer. So it's an end-to-end model. For that we need huge amount of data. But if it's not a end-to-end neural network even, we can train it on lesser data points, for example 1000, 10,000, 50,000, something like that. So why not? So we can start to learn all these things slowly, and we can understand what works and what doesn't, because again, all this is of heuristic knowledge, because we have to keep on experimenting, we have to keep on understanding what works and what doesn't. And what we do is we for constructing all these layers and everything, and deciding which one to keep, which one not to, and deciding other factors like hyperparameters of the model and all these things, we perform grid search, and we perform uh, backtracking and all these things, so that we can understand what works. So it's computationally expensive to perform all these tasks. So now let's understand more relatively closer topic than neural networks to machine learning. Getting back to it, so overfitting and underfitting, what is it? So whenever we are trying to train a model, what we are trying to do? So we are trying to tell it that you have to understand a certain set of rules, right? So we are giving it certain data points. All these are data points that we are providing to the model. Then this is the set of rule, right? This is the rule that actually governs these data points. So do you think that this is a good fit for these data points? No, right? Because it's too straight and all these points are getting missed, right? So all these points we don't want to miss. This rule actually doesn't fulfill our purpose of learning the rule, right? This line doesn't actually fit it. So we keep on training, because this is just training for a little while. We keep on training, and we go ahead and we see that the model has become like this, right? But can we actually see that model has learned the rule till a certain extent, that the rule looks something like this? Why are we calling this line rule? Let's first understand this. So y is equal to x square. What is it? It's simply a parabola kind of structure, or convex kind of structure, right? On a graph. So we are providing the value x, we are providing the answers y, we are training the model, and we are getting a mapping. So this graph, or this line on the graph, represents the fitting, or the rule of the model, right? The plotting between x and y, relationship between x and y. So that's why this line is the rule. And this rule, or this particular line, doesn't represent the rule of mapping between x to y. Just looking at the points that we have in the data, we can say that this line doesn't actually fit. So we have to look at the data to understand this. So when the model is training, constantly training, we don't know where to stop or where we'll get a good fit. So for example, if it keeps on training, how will we know that if the model is good enough now or not? Or should we train it more, or should we give it more data to train on? So we keep on iterating through the model, then we get something like this. And then if we keep on giving it more data, or giving it more chances to learn, what it will do is it will start to see that only these points are appearing on the graph. So let me just map myself to it. So now whenever I give it a new data, for example some data that is here on the x line, so it doesn't actually understand it. Why? Because it already has fitted itself to the available data points that we made it see, or we gave it to learn, right? But if it's learning a general trend, what we want to teach our model is the general trend. We don't want it to be 100% sure, but we want a certain level of surety that it will be somewhere very close to it what we are trying to predict. So why the y value here is very near to the curve. The y value again is very near to the curve, again here and again here, and some of those points already lie on the line or are touching the line. But here relatively more points are touching on the line, so whenever a new point comes, it won't understand it because the model is already adapted to the existing points and it's too stubborn to actually understand new points. Here the model is too flexible, and we don't want that level of flexibility because it hasn't learned anything at all. Because just take a look how relatively far these points are, right? But this model is actually balanced because it has learned the general trend and it hasn't overfitted or underfitted with the model, with the data that we are providing it. So these are the terms. When the trend isn't learned at all, it's called as underfitting, or learned relatively poorly, it's called underfitting. And when the trend is learned too well, or the rule is learned too well that it starts to map just on the input data, it's called as overfitting. So whenever we learn a general trend that governs this mapping, we call it a balanced model or a relatively good model that we want to actually work with, or we want to later use for predicting value of y given the value of x. So yeah, this is the basic concept of overfitting and underfitting of data. So this basically covers the various topics that I just wanted to discuss before getting into different models. So this will give you basic idea of how the machine learning models actually work and how we classify them, why we classify them, as all that. Then comes feature selection and extraction, which is just understanding which features work for our model and which features don't work. So if a certain feature works, like again, if I go back to the slide and show you the image example again, where we had to take the image, we had to understand how it's oriented, and again perform various operations over it, it would be called as feature extraction, because we want to actually extract the feature for our model to learn better, right? So these are relatively theoretical topics that I wanted to discuss in this module. So this was a relatively short module. Then we'll move to actually applying linear regression, and it will be simple linear regression and multiple linear regression. Both of these will understand what gradient descent is, and how it works, how our models learn using this. So this is going to be a word or a term that that you'll be hearing a lot when it comes to machine learning, deep learning, and all these things, because this actually is the very basic of how machine learning learns. This applies to all the machine learning models, and this uh, concept actually is what machine learning is based on. So yeah, we'll understand this, we'll understand maximum likelihood estimation, what is this, and yeah, that would cover the next module. So see you then.